Hello, students. So, the remaining goal in this class is going to be that power series converge on the domain where you remember that they converge on some so-called interval of convergence, and also to show that at least on the interior of that interval of convergence, the functions given by power series are continuous. So you remember, power series are things like, I don't know, let's use one of the ones from the example from the previous section. There's an example of a power series. And let's even think about what we did on the in the previous homework, I think. You showed that this converges uniformly on negative a half to a half. And how did you do it? Well, the rough sketch of what happened is you used the fact that absolute value of x to the k divided by k is going to be less than or equal to 1/2 to the k, because x is in here. And, well, because you know that, you could somehow use the fact that the sum of all of these 1/2 to the k's converges. And since you could pull all of that off, what did, like, some not so complicated stuff resulted in the sequence of partial sums. Was uniformly Cauchy, and so was uniformly convergent. And so all that this first video is going to be is taking that idea, making it explicit, proving that whenever you can put something here so that this converges, you can get that the series of functions that you're studying converges uniformly. So let's do some setup, write down some definitions. Suppose that fn is a sequence of functions. Then we'll say the series from k equals 1 to infinity of f sub k of x is the function given by the limit of the sequence of partial sums. So the sequence of partial sums, the nth one of those functions, is given by s sub n equal to sum from k equals 1 to n of f sub k of x. Its domain, by it in this case I mean the domain of the series, is the set of all x's in use, so the set of all inputs for which this series converges. And notice, once you fix a u, that's a series of numbers. You know what it means for that to converge. It means that the sequence of partial sums converges. If the sequence of partial sums, which remember is a sequence of functions, converges pointwise or uniformly, then I say that the series converges pointwise or uniformly. There should be no surprises in the definitions. Those are all the things that you would intuit if I just said the series converges uniformly. So here's the main result of this section, theorem 4.4.2, the Weierstrass M-series test. Suppose that f sub n is a sequence of functions, that m sub n is a sequence of numbers, that the absolute value of f sub n is less than or equal to m sub n for all x in u and maybe also all n in n, though you can probably intuit that the sum from k equals 1 to infinity of the m sub k's converges, then s sub n, no s sub n there, then the series converges uniformly on u. So let's go ahead and do that proof. As I said, this should feel pretty familiar to the ideas that were used in the homework from the previous section. Suppose that f sub n is a sequence of functions, that m sub n is a sequence of numbers, that f sub n is less than or equal to u for all x in u and n in n, and that the sum of all of the m sub k's converges. We need to show that the sequence of functions given by s sub n equal to the sum from k equals 1 to n of f sub k of x converges uniformly on u, right? Because that's what it means for the series to be uniformly convergent. But I know how to prove that a sequence of functions is uniformly convergent even when I don't know what the limit should be, which in some sense I don't. Right? If I were to even write down the sum from k equals 1 to infinity of f sub k of x, that would be assuming that and declare that that existed. That would be assuming that the series converges, which I need to prove. So I can't talk about the limit directly, but that's okay. I have this equivalent condition called the Cauchy criterion. By the uniform Cauchy criterion, it suffices to show that this sequence of functions, S sub n, is uniformly Cauchy. So if you like, that's just the want to show. That's what I will try to show. And what do I know? I know that the sequence of functions t sub n, the sequence of partial sums of m, the sum of the series for m sub k. So that'll be t sub n is the sum from k equals 1 up to n of m sub k. If that, since I know that the series of all of the mk's converges, it follows that t sub n converges, right? Because that's what it means for a series to converge. It means that the sequence of partial sums converges. And notice there's no such thing as talking about uniformly or pointwise because it's a sequence of numbers, not a sequence of functions. So that by the Cauchy criterion, t sub n is Cauchy, right? Convergent if and only if Cauchy. So here I'm using the reverse direction. And the motivation for that is I want to show that this sequence, S sub n, is Cauchy. And I have something that I should probably be able to use to compare S sub n's with T sub n's. So I'll use that T sub n is Cauchy to try to show that S sub n is Cauchy. All right, so now let's try to get Cauchiness. So here will be the sketch. You have to start by considering any epsilon bigger than 0. Then you come up with a choice of big N. Well, this is the only thing that I know is Cauchy, so I'll use that to come up with my choice of big N. I'll then consider any m and n bigger than big N. Without loss of generality, I'll assume that one is bigger than the other. I think I assume m is bigger than... No, I think n is bigger than m is what I will assume. And then I'll just do the same things as you did a few times in the homework for specific examples, but for a general choice of f sub n's. All right, so let's do it. Consider any epsilon bigger than 0. Since t sub n is Cauchy, it follows that there exists some big N such that for all m and n bigger than big N, absolute value of t sub n minus t sub m is less than epsilon. Neato. So we've just come up with our choice of big N. So let's use that choice of big N. Once we come up with the choice of big N, we need to consider any little m and little n bigger than big N and any x in u. We want to show that the absolute value of s sub n of x minus s sub m of x is less than epsilon. Now, notice that's a sequence of partial sums, that's a sequence of partial sums, so a bunch of terms between those two things will cancel. That'll happen in this step. In order to make it clear what the cancellation will look like at the end, let's assume log, without loss of generality, log, that little n is bigger than or equal to little m. One of them is the bigger of the two, may as well be m. So let's use that. Let's use that assumption. Now, absolute value of s sub n minus the absolute value of s sub m is the sum from k equals 1 up to n of f sub k of x minus the sum from k equals 1 to m of f sub k of x. By the definition of s sub n, right? This is s sub n, that is s sub m. And you know what? I actually think here's what I want you guys to do. Pause the video, complete this proof, it's super straightforward, and then come back and maybe watch the rest of it at like 2x speed. It'll probably be faster for you anyway to do that. Okay, cool. So you guys have completed the proof. I'll now complete the proof, but I talk slow and I say a lot, especially when talking to the screen, I think. So let's just do it. Let's cancel some common terms. I know that all of these terms are also terms in that sum because little n is bigger than little m. So this will reduce to the sum from k equals m plus 1 up to n of f sub k of x, absolute value bars. By the triangle inequality, I can move those absolute value bars to the inside. Now notice, one of the assumptions of the theorem is that f sub k of x is less than or equal to m sub k. Let's go ahead and say it like this. No, k's are fine. I know it's stated in the assumptions with sub n's instead of sub k's, but that's okay. In fact, absolute value, right? So that means I can replace all of those f sub k's with m sub k's, make the whole thing a little bit bigger. So that's less than or equal to the sum from k equals 1, sorry, m plus 1, up to n of m sub k. And now, well, we can put some things back. That's the same thing as the sum from k equals 1 up to n of m sub k minus the sum from k equals 1 up to m of m sub k. Oh, but hey, that's exactly t sub n minus t sub m, which is less than or equal to absolute value of t sub m minus t sub n. Ah, but m and n are both bigger than big N. I know that whenever little m and little n are bigger than big N, the difference between t sub n and t sub m is less than epsilon. So that is less than epsilon because little m and little n are bigger than big N. Let's just put down a concluding sentence now. Thus, for all epsilon bigger than 0, because we started by considering any epsilon bigger than 0, we then came up with a choice of big N, such that for all little n bigger than big N, and for all x in U, absolute value of s sub n of x minus s sub m of x is less than epsilon. So s sub n is uniformly Cauchy. And so uniformly convergent, implying that the sum from k equals 1 to infinity of f sub k of x is uniformly convergent. Cool. So the remaining thing to do is just do some applications of this result. So let's start with this. Here's a series of functions. The sum from k equals 0 to infinity of the cosine of 3 to the k of 1 over 2 to the k times the cosine of 3 to the, well, what's written. We'll read what's written. So we will prove that that function is continuous on all of the real line. And this function has a special place in the history of analysis. This is the so-called Weierstrass monster function, or rather an example of it. And it's called the monster function because it has a really violent property. It's continuous everywhere. On the whole real line is it continuous, basically by the Weierstrass M test. But here's the graph of the 100th approximation of it. It looks really, really, really spiky, and I can't zoom in much, right, because that's just a screen grab. But you'll notice that, like, every point it looks like there's a spiky bit. So this function has the property that it is not differentiable anywhere. So it's even worse than things like absolute value of x, which have a single point where they're not differentiable. It's not differentiable anywhere. We won't be able to prove that, because we haven't even really said what the derivative is. So maybe I'll leave that to you to think about, proving that this thing is not differentiable. There are some good discussions out there. Maybe it'll be one of the optional final projects. So let's talk through the proof that that function is continuous. So let's let f sub k be 1 over 2 to the k times cosine of 3 to the k times x, and m sub k be 1 over 2 to the k. Now, there's a reason that I chose that for my m sub k. So think to yourself, if I add up all of those m sub k's in a series, do I get something that converges? Sure do. I get a geometric series. Geometric series converge. Is that m sub k bigger than or equal to the absolute value of that f sub k? Sure is. Absolute value of cosine is just between, is at its biggest, 1. So f sub k of x is going to be less than or equal to 1. So let's say that since absolute value of cosine of x is less than or equal to 1 for all x, we can conclude that the absolute value of f sub k of x is less than or equal to m sub k for all k. Let's not even say m sub k. Oh, absolute value of f of k. The absolute value of 1 over 2 to the k times the cosine of 3 to the k x is less than or equal to 1 over 2 to the k. By the geometric series test, the infinite sum of all of the 1 over 2 to the k's converge. Therefore, by the Weierstrass M test, this sequence of partial sums converges uniformly as n goes to infinity. So that means that not only does the infinite series exist because the sequence of partial sums converges, it's the uniform limit of a sequence of continuous functions. So we can conclude, because it's the uniform limit of a sequence of continuous functions, that the sum from k equals 0 to infinity of 1 over 2 to the k times the cosine of 3 to the k times x is continuous. And in fact, you could prove something better. It even turns out to be uniformly continuous. All that would require is to replace the fact that the uniform limit of a sequence of continuous functions is continuous with the fact that the uniform limit of a sequence of uniformly continuous functions is continuous. There's one last thing in this section, and namely it's this instruction. Use the Weierstrass M test to show that the series given by the sum from k equals 1 to infinity of 1 over k squared times cosine of pi times x to the k is continuous on all of R. In fact, what I'll encourage you to do is to grab a graph, and, well, you probably can't graph that function exactly, but you can graph the 100th, maybe the 1000th approximation of that function, and take a look at it. Does it look differentiable? Where does it look differentiable? Where does it not? You won't be able to answer the question about where it's differentiable because we don't even have the definition of differentiability to walk with. But take a look at that function. So maybe I'll give you as a hint. You have already proven that the sum from k equals 1 to infinity of 1 over k squared converges. Nice. So do that, and then come back for the next video in which we'll start talking about power series.